Hello and welcome to another one of D's ADD videos. Today we're going to be looking at this repeated root here. It came from the scenario of solving a characteristic equation. You got the repeated root of r plus 3, which when you set equal to 0 and solve, you get negative 3. Because of this 2, you write down e to the negative 3t plus te to the negative 3t. Actually, your general solution would have been of this form. So what we got to do here is set up the Wronskian. Then we got to prove that it doesn't equal to 0. And then we're done. It's a fundamental set of solutions. So if we have the derivative of y1, that would be the derivative of your exponent times what you had originally. Now on y2 we have a product rule because there's two t's being multiplied, so the derivative of the first times the second with no change plus the first with no change times the derivative of the second. So if we were to rewrite that in a neater form, we could factor out that e to the negative 3t and get 1 minus 3t. Had over factor to figure out what's left behind. So set up your Wronskian from that. So y1 goes in the first spot, its derivative below it, then y2 goes up here, and its derivative down here. Find the determinant. It's going to be this times this minus this times this, so it's going to be e to the 3, so this is w, this would be the determinant of w. Now when you multiply two like bases, you add the exponents, and then you have that 1 minus 3t. And then minus a negative 3t e to the negative 3t plus negative 3t again. So let's look at what we have when we simplify a little bit. We're going to have e to the negative 6t 1 minus e to the 3t plus 3t e to the negative 6t. So at this point we can factor out that e to the negative 6t. You could have just as easily distributed it through and combined your like terms, but I prefer factoring things out, and usually what happens is you end up with a lot simpler thing to deal with inside the parentheses, like we do here. To figure out what's left, you take all of this that you had originally, divide by what you're factoring out, that gives you this. All of that divided by this gives you that. A little basic algebra there. And then these two cancel out, and you're left with e to the negative 6t. Well, if you remember, there's no value that you can plug in for t to make this equal to 0. That never equals 0, right? Because there's an asymptote at y equals 0. So therefore, y1 and y2 form a fundamental set of solutions. Okay? Again, to satisfy that third condition, which I doubt you'll really have to do. Usually they just want you to use Wronskian to prove it's a fundamental set of solutions, and as long as you can say it never equals 0, they're satisfied. But I will do one more advanced condition problem in which you have to find out what the initial conditions are to make this little theorem satisfied, to formally make them a fundamental set of solutions, okay? Because technically the Wronskian never equaling 0 is just part of it, but the initial conditions must be met. So the Wronskian guarantees that you can use those two solutions to form a fundamental set of solutions. It exists, but you might have to figure out under what C1 and C2 values that those two actually do form a fundamental set. And I'll do an example of that you can check out, okay? I hope I've eliminated any doubts that you might have over the Wronskian. Again, just practice, practice, practice. You'll see it's not that bad. Just a few derivatives is the worst case scenario. Thank you and have a nice day.